The final glitch. Why scientists think the simulation is ending. What if reality just missed a beat? Two national labs compared their sharpest atomic clocks and saw a mismatch that shouldn't exist. Not noise, pattern. At the same time, ultra-high energy cosmic rays nudged a hard limit like they bounced off invisible latticework. And new black hole math whispered that a firewall might torch smooth space at the edge. That's not a movie, it's our checklist. Here's the plan. The first cracks in measurement, the universe's memory model, the rendering budget, and what fails first, the physics engine, or the UI. Stick around and you'll know how we catch a final glitch, and why it matters to you. Are we hitting the edge of the sim? Setup, peak drama, then rewind. Get this? The measurement didn't just fluctuate, it disagreed with itself. Two clocks built from different atoms, calibrated by people who live and breathe uncertainty budgets, synced to picoseconds, then drifted apart in a way that lined up with sidereal time, not lab time. Nobody declared victory over the constants. They did what scientists do: tighten cables, rebuild shielding, rerun months of data. The drift shrank, then returned. Meanwhile, a collaboration studying ultra-high-energy cosmic rays sketched a suspicious bump near a hard limit, like there's a maximum detail level the cosmos refuses to render beyond. Over in black hole country, page curve style calculations said information can get out unless a searing firewall blocks smooth space at the edge. That's an access denied banner at the boundary of reality. Visual. Split screen. Clocks. Cosmic ray air shower. Black hole horizon. Rewind. Simulation talk isn't just video game banter. It sticks because physics keeps finding ceilings and compression tricks. There's a maximum speed for information, light, set by relativity. There's a regime where our theories sputter, the Planck scale. Black holes store information like area, not volume, as if the universe budgets bits per square meter. None of this proves code. But constraints everywhere beg a question. Are we inside a system with a finite compute budget? Honestly, it's like trying to run Elden Ring on a toaster. Tiny fan wine. The stakes aren't abstract. If observation helps make outcomes real, who's doing the right? If entanglement is correlation without contact, what counts as nearby? If clocks only agree within a tolerance, what happens if that tolerance breathes? Your everyday world, the solid, continuous, predictable, might be a user interface built from redundancy and error correction. That's good news until the redundancy gets thin. So here's our through line. In a constrained universe, what ends first? The physics engine that resolves states, or the render pipeline that presents a smooth world? If the engine falters, edge experiments, deep quantum, extreme gravity, ultra-high energy, start returning results that look self-contradictory, then settle into cheaper rules. If the render pipeline flickers, stability fails where consensus is built, distributed timekeeping, reference standards, long baseline correlations. Labs recalibrate more often, and the fixes work, until they don't. But before the end game, we need the first cracks. The quantum measurement problem isn't a cute paradox. It's where reality waits for instructions. Double-slit weirdness, Wigner's friend, delayed choice. Moments where outcomes don't decide themselves until someone asks. If that's a compile step, we have to ask, what's the universe's memory model, and how does it behave under load? Systems fail at their bottlenecks. Measurement is where the bottlenecks begin. The first crack, quantum measurement paradox. Start with the slit. You send single electrons, one at a time, through two narrow openings toward a screen. If no one checks which slit each electron chose, the screen builds an interference pattern, bright and dark bands like ripples crossing. But place a detector at the slits to learn which way, and the pattern collapses into two fuzzy blobs. Same electrons, same apparatus, one difference. You asked a question. The result changed. That's not a metaphor. That's the experiment. The stakes are heavy. If outcomes depend on questions, reality waits for instructions. Now scale the question. Wigner's friend turns a lab into a character. Inside a sealed room, a friend measures a quantum system and writes "up" in a notebook. Outside, Wigner treats the whole room, friend, notebook, apparatus, as one quantum state, still in superposition. Both descriptions can't be true in the same way. So when does the measurement happen become a fact? At the click of the detector? When the friend looks? When Wigner learns, if the compile step is delayed, the world holds two versions of events. Somebody's real isn't globally real yet. Wheeler's delayed choice adds a twist. Decide after a photon passes the slits whether to measure its path or its interference, and the outcome still respects your late decision. From our perspective, it's like the system keeps alternatives alive until the very last compatible moment, then writes a single consistent history. That's not retrocausality in the usual sense. It's consistent with quantum rules. But as a story about how realities become real, it reads like just-in-time compilation. Don't render the path until the scene needs the path. Physicists don't shrug at this. They build experiments that push the boundary, weak measurements that barely disturb systems, delayed choice entanglement swapping, where correlations appear between particles that never coexisted, nested interferometers that force you to admit a particle can leave breadcrumbs where it apparently never traveled. Each result lands inside the quantum formalism, but the human questions pile up. Where is the line between possibility and fact? Who draws it and when? There's a pragmatic answer: decoherence. Interactions with the environment entangle the system with countless degrees of freedom. The off-diagonal terms, those delicate superpositions, bleed into surroundings and become effectively unobservable. In practice, that means the world looks classical, because interference between macroscopically different states gets washed away insanely fast. It's the best broom in physics. But it doesn't pick a single outcome. It hides alternatives in correlations we can't access. The paradox doesn't vanish. It becomes a bookkeeping problem. Where is the record of what happened? If you're thinking like a systems engineer, the metaphor is tempting. Measurement is a right to stable storage. Before the write, variables can live in registers, cheap, reversible, superposed. During the write, the system commits to a branch. If the universe is a finite machine, commits might be throttled, batched, or rolled back under load. Labs chasing quantum advantage feel this daily. Qubits are fragile. To measure, you integrate weak signals over time, reject noise, and still risk collapsing states you wanted to keep. It's not mystical, it's cost. Then there's Wigner's friend-style consistency under observers. In a perfectly isolated thought experiment, two observers can assign different states to the same system and both be right within their frame. The consistency constraint is that when they compare notes, outcomes must align. In compute terms, that's eventual consistency. Local views can diverge. Global reconciliation reconciles them, but at a cost in bandwidth and latency. If reconciliation fails, we'd expect contradictions. I saw up, I saw down, both backed by perfect logs. That hasn't happened. The constraint is ironclad, but it raises the resource question. What guarantees the merge? Now bring in the delayed choice experiments that couple light years of path length to a late switch. Signals still respect light speed, but the correlations hang together. No influence crosses faster than c. The global quantum state simply encodes the right constraints from the start. It's elegant, unless you're tracking resources. Encoding those constraints across vast distances without a physical substrate carrying a classical message looks like a pre-computed consistency plan. It's fine if the plan rides on the wave function. It's expensive if you imagine a simulator faking it after the fact. Counterpoints matter. Many world says there's no special compile step, just unitary evolution, branching observers, and local experiences of a single outcome. Bohmian mechanics gives definite particle positions guided by a pilot wave. Objective collapse models bake in a tiny chance of stochastic collapse that scales with mass. Each resolves some discomfort. None removes the empirical core. Outcomes sharpen when measured, and the sharpening obeys rules that treat information as physical. As Rolf Landauer put it, information is physical. You pay to erase a bit. You pay to write one too. Here's the crack then. As experiments scale, from single photons to mesoscopic molecules, from tabletop interferometry to satellite tests, keeping superpositions alive gets exponentially harder. That's expected from noise. But watch the pattern. Every time we push the Heisenberg boundary, we're negotiating with a system that resists clean, late writes. If measurement is commit, then high complexity commit should be the first place a finite engine shows strain. That strain wouldn't look like magic. It would look like tiny biases under specific loads, weird but replicable edge case failures, or statistical anomalies that vanish when you reduce complexity. What nobody knew at the time we first drew those interference fringes is how far we could push the compile step before it breaks. We still don't know, but the next clue lives right next to measurement: memory. If measurement writes, where do the writes go, how are they indexed, and what happens when pointers cross scales? Entanglement already hints that memory isn't local. So we go there next. The universe's memory model, error rates, and what it costs to keep the ledger straight. Memory leaks, entanglement, error rates, and quantum limits. Start with the weirdest shared notebook you'll ever meet. Take two photons born together in a crystal. Measure one here, the other across town, and their results line up in ways no local story can explain. That's entanglement. Correlations that don't care about distance, yet never send a usable signal faster than light. Labs prove it daily with loophole-free Bell tests. If measurement is a right, entanglement looks like shared pointers, two variables referencing the same underlying record. Change how you read one, and the joint record constrains the other. Nobody's cheating causality. The correlations are baked into the state. But shared pointers invite bugs. In code, if a pointer outlives what it points to, you get a dangling reference. Physics version: let entangled qubits sit in a messy environment, and decoherence starts chewing through their fidelity. The joint record is still there in principle, but practically it's smeared into the noise of the world. That's why every quantum lab sounds like a reliability engineer. They talk in error rates, T1 and T2 times, leakage out of the computational basis, crosstalk between lines. Keep the qubits cold, shielded, isolated, and they still wander. Errors don't hate us, they just outnumber us. Quantum error correction is the counterspell. You don't trust a single physical qubit. You spread one logical qubit across many, entangle them, and measure stabilizers to detect flips without collapsing the encoded information. It works, but it's brutally expensive. The surface code, today's workhorse, demands thousands of good enough physical qubits to make one robust logical qubit for non-trivial algorithms. And good enough means gate fidelities above tight thresholds and fast, repeated syndrome extraction. Every cycle is a bet that you can catch and fix errors before they pile up. Here's where the universe starts to look like it has a fidelity budget. When we scale devices, we see patterns. Crosstalk grows with wiring density. Noise sources couple in new channels. Control pulses bleed into neighbors. Materials sprout two-level defects that flip with temperature or stress. Superconducting circuits hit one set of walls. Trapped ions hit others. Laser intensity noise. Motional mode crowding. Micromotion. Neutral atoms bring their own gremlins. Spontaneous scattering. Imperfect blockade. Different platforms. Same feeling. The larger the entangled state, the tighter the timing, the thinner the margin. Honestly, it's like hosting a dinner for 4 and 50 cousins show up. Crowded table, spaghetti of cables. Meanwhile, in simple, classical-looking systems, everything's beefy. Your phone's bits are robust. A metal bar remembers its length well enough for engineering. Classical UI tolerates abuse because redundancy is everywhere. Many degrees of freedom average out noise. Error modes get damped. But down where entanglement lives, redundancy cuts both ways. The same coupling that lets you knit qubits into codes also gives the environment 1,000 ways to pull threads loose, so you build more code. That means more qubits, more cycles, more chances to leak. It's a treadmill with physics setting the incline. Physicists map this treadmill in numbers. Coherence times sit at microseconds to seconds, depending on platform. Gate fidelities creep from 99% to 99.9 something. Every extra 9 is expensive. Fault tolerance thresholds promise salvation above a certain line, but they're asymptotic. They tell you scaling is possible, not free. And lurking under the dashboards are non-Markovian tails, memory in the noise. If the errors aren't independent and identically distributed, your fancy thresholds wobble. Nature has a long memory. Materials age. Drift. Now tie that back to entanglement as a memory model. In the fundamental theory, entanglement is the bookkeeping of reality. It tracks who's correlated with whom, so that when you read one log, it's consistent with others. If the universe is finite compute, that bookkeeping might be bounded in practical fidelity. Not a conspiracy, just a cap on how cleanly global constraints can be maintained as systems get larger, colder, and more intricate. If there's a memory leak anywhere, it appears where the ledger is densest. Large-scale entanglement, long baseline correlations, high-depth circuits. We've already seen hints of scaling strain. Multi-atom entangled states, GHZ cats with dozens or hundreds of atoms, fragilize as n grows, phase noise scales with n, and contrast falls. Boson sampling experiments with many indistinguishable photons show output distributions that drift under tiny component imperfections, making certification tricky. Scrambling experiments that measure out-of-time order correlators need exquisite control. Small calibration slips look like physics. None of these are final glitch alarms. They're reminders that pushing entanglement is a fight against an exponential surface area of ways to fail. Quantum error correction tries to buy us headroom, and it works, until overhead eats the budget. Logical cycles grow, cooling loads rise. Classical side processing for decoding syndromes becomes a bottleneck. You can offload to faster electronics, but then you hit heat and latency. It's turtles all the way down, and every turtle costs watts, bandwidth, and time. In a simulation frame, this is where the analogy sharpens. Sustaining high-fidelity, non-local correlations at scale is the most compute-hungry thing you can ask a universe to do. If a runtime trims load, it trims here first. So what would a real memory leak look like to us? Not Hollywood glitches, no pixels falling off the moon. It would be subtle, targeted, reproducible weirdness in high-complexity quantum tasks. Correlated error bursts that don't fit noise models. Syndrome patterns that imply impossible coincidences. Fidelity plateaus that won't budge past a boundary despite materials and control improvements elsewhere. You'd see anomalies that vanish when simplified. Turn off 3 couplers, shorten the circuit, reduce N, and the ghosts leave. Meanwhile, the classical layer stays smooth because it's cached. Nature's UI pointer states that decohere into redundancy hides small fidelity losses behind consensus. That's the tell. Fragility below, robustness above. If entanglement is our window into the ledger, then its error rates are our first read on the universe's limits. And if those limits bind harder as we scale, the crack we felt at measurement widens into a budget line. A bound on how coherent the world can be, for how long, across how much space. That budget doesn't end the story, it sets up the next one. Because a bound on coherence looks a lot like a bound on detail. And at cosmic scales, bound on detail lives on horizons. Black holes, bit counts, and the strange rule that area, not volume, measures information. If entanglement is the ledger, horizons are the ledger's edge. Now we ask, how many bits fit on a boundary, and what happens when the world tries to write more? Rendering budget, holographic principle, and bit limits. Here's the jump. From fragile qubits on a chip to the hardest cap the universe seems to enforce. How many bits fit on a boundary? Black holes force this on us. Toss matter in, and you'd think its information content should scale with volume. But Jacob Bekenstein did the accounting and found a different rule. The maximum entropy inside a region is proportional to the area of its boundary, measured in Planck units. Then Stephen Hawking gave us a temperature and an evaporation rate, and entropy followed the area law exactly. That's a budget, not a vibe. If entropy is the count of microstates, the number of distinct configurations compatible with what you see, then the area law says, you don't get infinite backstage detail just by stacking stuff inside a region. The boundary, its surface, sets the cap. That's weird until you treat it like storage. Nature doesn't pay for bits in the volume, it pays for bits on the surface that encloses the volume. The Bekenstein bound generalizes this. For any system with energy E in a sphere of radius R, the information content is bounded. Blow past it and you collapse into a black hole, which resets you to the area budget. Leonard Susskind and Gerard 't Hooft took the hint and said it out loud, holography. A full 3-dimensional world can be encoded on a 2-dimensional boundary. Not as a trick, literally equivalent physics. The sharpest lab for that idea is AD-SCFT. A gravity theory in a bulk space is exactly dual to a quantum field theory on its boundary with no gravity. Different languages, same story. Calculations done on one side translate to the other, including black hole thermodynamics and quantum entanglement structure. It's a dictionary for how space-time could be a compression of deeper information. Now bring back our runtime metaphor. If the world's detail is capped by surface area, you get a rendering budget. There's only so much state the universe can track inside a region before the boundary saturates. Smooth experiences are still possible, just like a game looks smooth at 60 frames per second, but you can't exceed the memory cap without reducing resolution, culling distant detail, or offloading. Holography says the offload target is the boundary degrees of freedom. The disk is the horizon. Scientists don't all agree on what holography means for our universe because as space-time isn't our cosmology. But the area law keeps showing up. Entanglement entropy between regions and ground states follows area scaling. Quantum error-correcting codes turned out to be the right math to model bulk boundary relations in toy holographic models. You can literally draw a tiling where each boundary tensor stores and protects bulk information in a way that mirrors how error correction works on a chip. Less is more because redundancy lives on the edge. Here's the sticking point. We walk through a world that feels continuous, with insane detail at every glance. How does a capped bit budget produce that? Two moves make it work. First, compression. Physical law is simple and local enough that you don't need to store every pixel. You generate appearances from rules. Second, redundancy. The classical UI repeats the same facts across many degrees of freedom. Your coffee cup's position is encoded in zillions of atoms and in the light bouncing off it. That redundancy makes it feel crisp, even if the underlying ledger uses fewer compressed bits than your eyes think. But compression isn't free. The smoother the fields and the cleaner the symmetries, the cheaper the description. When fields get turbulent when you stack complexity, the compressed description expands. That's a compute tax. If the bit cap is hard, area, and the compression demands spike, the runtime can't just mint new storage in the bulk. It has to shuffle detail to the boundary, drop resolution somewhere, or slow the rate at which new independent detail accrues. From our side, that could look like fewer long-range correlations, harsher decoherence, or hard limits that show up as thresholds we can't cross without gravity answering. Think about cosmic horizons. The observable universe has an apparent boundary. Beyond a certain distance, light hasn't had time to reach us. That boundary comes with an entropy. The Gibbons, Hawking story for de Sitter space ties a temperature and an area to cosmic horizons, echoing black holes. If horizons carry entropy, they carry storage. Then the budget becomes global. As the universe expands, the boundary area changes, and so does the total room for independent detail. That's not mystical. It's bookkeeping in a space-time that treats information like a physical commodity. Here's where the human struggle shows. Theorists love clean caps. Experimentalists love continuous curves. Between them sits a daily engineering question. How do you get smooth macro scales from cap micros? The answer they're converging on uses entanglement as the glue and quantum error correction as the blueprint. Space-time geometry might literally be the way entanglement patterns organize. Cut entanglement, geometry frays. Increase it, geometry knits tighter. The boundary code protects the interior from small errors, like a RAID array for reality. Complication time. If nature runs on a cap, why don't we see chunky pixels at the Planck scale? Because the cap isn't a grid, it's an inequality. You can approach it with black holes. In normal stuff, you're far under the budget. Smooth fields spread information, and the redundancy buys you fidelity. The cap bites when you try to concentrate detail, pack too much entropy into too small a region, or when you stretch correlations across horizons. That's why the limits show up at extremes, not in your kitchen. So what's eating the budget? Growth in accessible volume doesn't help if the horizon's area and the rules of expansion bottleneck information density. If you wanted to keep the sim cheap, you'd lower interaction density as the cosmos grows. That's exactly what cosmic acceleration does. It pulls distant regions out of causal contact, reducing the need to maintain long-range entanglement, which means our next suspect isn't a particle, it's the engine of expansion itself. Why is the universe speeding up, and what does that do to the ledger? While that boundary story plays out on horizons, something else is happening everywhere. The fabric is speeding up. Galaxies aren't just coasting apart. Their separation accelerates. We call the driver dark energy. It acts like a uniform pressure baked into space, the cosmological constant lambda in Einstein's equations. You don't feel it. Over billions of light years, it rules. In a runtime frame, this looks like a scheduler decision. Reduce crosstalk by stretching the grid, so fewer nodes need to stay in sync. Here's the physics first. When astronomers measured type Ia supernovae in the late 1990s, their light curves and redshifts said distant explosions were dimmer than expected for a slowing universe. The inference, Expansion is accelerating. Independent lines, baryon acoustic oscillations, the cosmic microwave background, locked it in. The simplest fit is a constant vacuum energy density. Every cubic meter of space carries the same energy, so as space grows, there's more of it. Gravity from matter tries to pull together. This term pushes apart. Then the fiasco. Quantum field theory naively predicts a vacuum energy that's absurdly larger, by about 120 orders of magnitude, than what we infer. That mismatch is the cosmological constant problem, one of the worst fine-tuning puzzles in physics. You can view it as a theory failure, or, in our metaphor, as a system that found a tiny, precise knob setting to keep the runtime stable. Either way, the observed lambda is small, positive, and relentless. Over time, it wins. On-screen text. Vacuum energy, predicted versus observed per quadrant 10 to the power of 120. What does acceleration do to information flow? It creates and inflates horizons. Regions that can talk now won't be able to in the far future, because light from there will never reach here. Entanglement across those would-be boundaries becomes harder to maintain dynamically. Correlations decay from our perspective. If the ledger of reality pays a cost to keep distant degrees of freedom consistent, acceleration is a coupon. It slashes the number of pairs that need active upkeep. The universe chooses low graphics mode at scale, not by dropping frames where you live, but by pulling far scenes off the render list. Now stay honest. Cosmologists don't frame lambda as a compute optimization. They model it as a stress energy component with negative pressure and test whether it's constant in time and space. So far, data prefers boringly constant. People explore alternatives, quintessence fields that roll slowly, modified gravity that tweaks Einstein on large scales, back reaction from inhomogeneities. Those aren't fringe, they're live research programs. But the observational story today says, a smooth, uniform term fits best. Smooth terms are cheap to describe. That's compression friendly. Meanwhile, the cosmological constant problem hangs like a comment thread nobody wants to moderate. Why is the vacuum energy so small yet non-zero? Supersymmetry could cancel contributions if it were unbroken. It's broken. Anthropic arguments in a multiverse say observers only arise in pockets where lambda is small enough to allow structure. That's a selection effect, not an explanation. In our runtime lens, this looks like a global parameter that sets the long-term compute bill. Set it too high, nothing binds, cheap but empty. Too low, everything collapses, expensive and short-lived. Narrow middle band, structure forms, then gets gently cordoned off. Here's where the budget theme sharpens. As expansion accelerates, average matter density drops like a power law, while vacuum energy density stays constant. Interaction rates fall. Long chains of causal influence get cut. From the ledger's point of view, there's less new independent information being generated that must be tracked across vast distances. Locally, chemistry, stars, life, all the rich compressible stuff keeps burning through free energy. Globally, the rate at which new, unconstrained correlations appear is throttled. You're not seeing pixels, you're seeing the scheduler cap throughput. Is there a signature of this throttle? One place to look is in the distribution and growth of large-scale structure. Surveys map how galaxies clump over time. If dark energy is truly a constant, the growth history follows a precise curve, and deviations could hint at different physics, or, speculatively, at a runtime that adapts. Another is in the cosmic microwave background's late-time integrated Sachs-Wolf effect. Changes in gravitational potentials imprint subtle temperature shifts if expansion accelerates. We've seen hints consistent with lemlim. Not everyone agrees on the significance, but the direction matches. Potentials decay. The background carries the receipt. Humor break. You can't hear in a grant proposal. It's like the universe looked at its monthly bill and turned off 4K streaming for the outskirts. Nearby, your show plays fine. Far away, the algorithm downscales, then stops preloading entirely. If you try to sync with the edge, you get buffer wheels. Midge flicks, style spinner over a star field. Alternative frames still matter. Modified gravity could mimic a cosmological constant without vacuum energy at all, reassigning the cost from storage to rules. Some data tensions. The Hubble constant measured locally versus inferred from the early universe. make people wonder if late-time physics differs slightly from the textbook model. That's where the resource drain story can stay, as a metaphor while we follow the data. If a new field drives acceleration and slowly changes, it changes the budget in time. If gravity itself changes, the cost of enforcing consistency might shift with environment. Bring it home to our arc. Whether lambda is a constant, a field, or a tweak, acceleration reduces cross-region coupling. If a finite engine is juggling constraints, that's the cheapest way to survive long-term. Push subsystems out of contact, lower maintenance, prevent global cascades. And if the runtime ever needed to offload detail, the natural sinks are horizons. Black holes most of all, which means the next stop isn't optional. We have to stare at the places where information goes dark and ask, is that garbage collection or a vault with a key we don't yet hold? Black holes, garbage collection, or data vaults? Stand at the edge where gravity turns sentences into whispers. You drop a book into a black hole. From far away, you watch it redshift, slow, smear, and fade. If nature is neat, the words are gone. If nature is consistent, the words are somewhere. That's the paradox that haunted physics for decades. Hawking's calculation said black holes radiate like hot coals and eventually evaporate, but the radiation looked thermal, featureless. If the hole dies and the outgoing light carries no imprint of what fell in, information disappears. Quantum mechanics hates that. Unitarity says processes evolve without tossing information. So who pays the bill? Jacob Bekenstein had already taught us to count in area. Black holes have entropy proportional to their horizon area, and Hawking gave them a temperature. That alone hints the horizon stores bits. Don Page sharpened the argument. If a black hole starts in a pure quantum state, the entropy of its radiation should first grow and then fall as the hole shrinks, tracing a Page curve. Early radiation looks thermal. Later radiation carries correlations that encode the lost detail. If you can catch every photon, you can in principle reconstruct the book. That's a vault, not a shredder. For years, we couldn't see how that curve could emerge from Hawking's calculation. Then newer tools from quantum gravity, replica wormholes and island formulas, suggested a way. The entanglement wedge of the radiation can include a chunk of the interior. In plainer words, the bookkeeping region that counts information in the Hawking light isn't just outside, it somehow reaches in. The Page curve pops out right where you expect it. Information doesn't vanish, it takes a weird route. It's still speculative in places, but it meshes with holography and with unitarity. The ledger balances. Now overlay the runtime frame. Garbage collection frees memory without losing data the program needs. You mark what's still referenced, sweep the rest, and keep the system responsive. If black holes are cosmic GC, they compress incoming mess onto the horizon's degrees of freedom, trickle it out as correlated radiation, and free capacity. That's elegant and ruthless. The event horizon is the boundary where the runtime takes over. Outside, fields play by local rules. At the boundary, compression and error correction dominate. The Bekenstein-Hawking area is the heap size. Then came a punch, the firewall. Almhiri, Marolf, Polchinski, and Sully asked whether late-time Hawking quanta can be maximally entangled with both the early radiation and with interior modes that guarantee a smooth crossing for an infalling observer. Monogamy of entanglement says you can't have both. If unitarity holds and an external observer can, in principle, decode the interior from the radiation, then the interior partner's entanglement is broken. Instead of no drama at the horizon, you get a wall of high-energy quanta, a firewall. Smooth space fails at the edge. It's an access denied sign that burns. Nobody liked that outcome. General relativity promises a boring ride for a big black hole, so people hunted for escapes. Maybe subtle non-locality lets interior and exterior share structure without cloning. Maybe complementarity. Different observers tell compatible stories without a single global description. Saves the day. Maybe quantum extremal surfaces and islands shift what we count as interior in a way that respects both smoothness and unitarity. The debate's still live, but the broad tide has moved toward unitarity with sophisticated bookkeeping, not brute destruction. Whichever side you favor, timing matters. If the radiation starts carrying detailed correlations around the page time, the halfway point in evaporation, then there's a schedule. Early on, The hole looks like a near-perfect thermalizer, a fast scrambler that hides input quickly in microscopic degrees of freedom. Later, the output isn't just heat, it's code words. That's precisely how an efficient GC behaves. It absorbs, compacts, and releases in phases, ensuring the global state remains recoverable if you have the map. What would a hiccup look like? If the garbage collector stutters, you don't see fireworks in your backyard. You detect tiny timing anomalies in processes tied to horizons, echoes and gravitational wave ringdowns that suggest structure at the boundary, slight deviations from the no-hair spectrum that shouldn't be there, or correlations in Hawking-like emissions in analog systems that don't match perfect thermality. LIGO and Virgo have hunted for echoes. Evidence is tentative at best. Analog black holes in fluids show thermal emission analogies, but they're analogies, not proof. The door is cracked, not open. Let's be real. If nature's hiding something here, it's shy. Quiet door creak. Human angle. Generations of physicists argued in print and in hallways about whether nature would rather burn a falling astronaut or break quantum mechanics. Recent work, page curve recoveries via path integrals, and the discovery that holography behaves like a quantum error correcting code, gives a middle path. The horizon is a code boundary. Smoothness for infallers is a feature protected by encoding, while outside observers can, in principle, decode with astronomical resources. It's not free, it's hideously expensive. But, in principle, is all quantum theory demands. Spin that back to our narrative. If black holes are data vaults that double as garbage collectors, horizons become the system's primary offload sites. Complexity goes in, is scrambled, stored at area cost, and returned in a long tail. That stabilizes the runtime. It also creates sharp edges where any resource stress would show first. If the encoding fails, you'd expect either leaks, information loss, or brute defenses, firewalls. Both would show up as timing glitches and spectral oddities at the edges, not in mid-space. The edges are where policy meets physics. And remember the expansion story. Accelerating space draws more and more of the universe behind horizons, cosmic and black hole. The runtime's offload capacity grows in boundary area, while bulk interactions thin out. From a compute lens, that's a graceful degradation plan. Trim long-range couplings, stash complexity on robust edges, and schedule slow returns. If something goes wrong with that plan, we'll know to look where the ledger is densest. The boundary of no return, where the world decides what it keeps and what it lets go. Timekeeping. Failures. Clocks, constants, and drift. While horizons hoard complexity, time tries to keep the receipts. The question is brutal in its simplicity. Do the rules tick perfectly? Atomic clocks are our sharpest knives. They don't count seconds like wristwatches. They count cycles of light emitted by electrons jumping between energy levels, different atoms, different frequencies. Strontium lattices hum in the optical, aluminum ions whisper even higher. Build two of these, isolate them, stabilize lasers to absurd narrowness, and you get agreement to parts in 10 to the power of 18 and beyond. That's like comparing the age of the universe to the blink of an eye and spotting a mismatch. Labs turn this precision into a hunting license. If any fundamental constant drifts, Planck's constant, electron mass, or the fine structure constant that sets electromagnetic strength, then the ratio between clock frequencies tied to different atoms will creep. You don't need to know which number moved. You watch the ratio. Strontium versus ytterbium, aluminum versus mercury, hydrogen versus everyone. The tests run for months and years, through seasons, tides, and earthquakes. If the universe breathes, it'll exhale into those digits. So far, the ledger looks stubbornly clean. The best limits say fractional drifts are smaller than about 1 part in 10 to the power 18 per year for alpha. That's not zero, but it's quiet. Meanwhile, people compare clocks across distance, not just time. Relativity says gravity shifts rates. Clocks run slower, deeper in a gravitational well. Move an optical clock up a centimeter and you can measure the change. Teams have done it. They lift time with a jack screw and watch frequency float. It's a party trick that doubles as a calibration of space-time smoothness. But quiet isn't the same as settled. There are long shots worth taking. Some astrophysical data, quasar absorption lines from billions of years ago, once hinted that alpha might vary across the sky. The claim is controversial. Systematics are everywhere in telescopes. New observatories and analysis methods raise and lower eyebrows in cycles. On the ground, next-generation optical lattice. Clocks push toward 10 to the power of 19 stability, and nuclear clocks, using the thorium-229 isomer transition that's unusually low in energy, promise a different sensitivity to variations. Put these side by side and you don't just hear time, you hear the constants humming. Here's where the simulation frame peeks in without breaking the rules. If a finite runtime started to strain, it wouldn't announce itself in the middle of clean averages. It would stutter at edges, at extreme precision, during synchronized operations, and in cross-platform comparisons where different physical mechanisms have to agree. That's exactly what global timekeeping is, a distributed consensus on the second. The Bureau International des Poids et Mesures blends data from labs worldwide into a timescale. Contributions arrive with noise, delays, and corrections. If the UI flickers, it flickers here first. Labs already design around human-level glitches. They account for cable delay, temperature gradients, magnetic field flickers, laser phase noise, servo bumps, and Earth's gravity changes as rain fills reservoirs. The discipline is part physics, part gardening, prune noise, water stability, harvest digits. What would a non-human weirdness look like? Not a big jump, a pattern, a sidereal modulation tied to Earth's rotation through some preferred frame, a correlation that shows up only when many labs run coordinated sequences, a persistent offset between clock species that survives every known systematic fix and scales with experimental complexity. There's precedent for time, acting like a seismograph for new physics. GPS had to bake in relativity to work. Without corrections, positions drift kilometers per day. Pulsar timing arrays use millisecond pulsars as galactic clocks to detect gravitational waves as nanohertz ripples that stretch and squeeze arrival times. Those arrays just announced a background consistent with giant black hole binaries. The method is simple. Watch for correlated timing noise across the sky. Replace pulsars with atomic clocks, swap space-time ripples for rule drift, and you're staring at a blueprint. To chase it, you need coordination. Imagine a time hack week where dozens of optical and microwave clocks lock to shared, cryptographically random schedules. They flip interrogation sequences in sync, vary environmental parameters on command, and publish blinded logs. A neutral beacon throws randomness everyone can verify later. If a global anomaly rides in, you'll either see correlated blips that line up with the schedule, or you won't. No single lab can fake it. No single lab can see it alone. World map with clock icons pulsing in sync. Now, honesty check. People are already watching. Frequency ratios are cross-checked obsessively. Transportable clocks climb mountains to compare with national labs. Fiber links braid countries into timing networks with femtosecond stability. No anomalies have survived peer review as physics yet. That's the point. The net is tight. If something slips through later, it'll be because we push precision and coordination hard enough to probe a quieter layer of the ledger. Parallel to clocks, constants hide in spectra and forces. Precision measurements of the electron's magnetic moment match quantum electrodynamics to a dozen decimal places. The Rydberg constant stitches together atomic spectra with astonishing consistency. The proton-to-electron mass ratio shows up in molecular lines. People check it in galaxies far away and long ago. Each test is a different ear to the same song. If the tune detunes, multiple ears should twitch. Vorschel, orchestra tuning, overlay of spectral lines. All of this lives at the boundary between quantum and classical. Clocks are quantum systems that we force to behave classically by reading them again and again, averaging away randomness until a phase becomes a number. That's decoherence as a service. It works because the environment writes copies of the answer into many channels: photons, phonons, electronics. If the copy machine slips, you don't see chaos, you see extra recalibrations. Fixes that hold for weeks start expiring in days. Checklists get longer. Trust migrates from devices to cross-checks. That's the human angle. People whose lives are measured in line widths will be the first to feel if time loosens. They'll log a weird frequency pool that tracks the stars instead of the sun. They'll swap boards, swap atoms, swap buildings, and a tick will keep its mind. It won't be proof of code, it'll be a symptom. And if it holds, it'll point at the next fault line, the place where the quantum becomes the world we walk through, where redundancy builds confidence and under stress shows seams. That line has a name we've used all along. The render line, decoherence, and the classical UI. Unknown to them, across town, Another lab was proving how the world chooses what to show. Decoherence is that choice dressed as physics. You take a quantum system, say a single atom with two energy states, and you let it touch the world. Not a lot. A whisper of stray photons, a jiggle of a phonon in the trap, a hint of fluctuating fields. Those soft touches entangle the atom with countless environmental degrees of freedom. The off-diagonal terms in its density matrix, the parts that carry superposition, get shared so widely that interference becomes unobservable. The system hasn't announced one outcome to the universe. It's just become impossible for you to access the phase relations that mattered. Now here's where it turns into a user interface. Wojciech Zurek called them pointer states, the stable configurations that the environment monitors on repeat. Position, low energy orientations, robust collective modes. The world measures those over and over by scattering light, exchanging heat, and vibrating structures. Quantum Darwinism extends the idea. The environment isn't just a sink, it's a broadcast network. Photons, air molecules, and solid lattices copy information about pointer states into many redundant fragments. You don't open a wave function to see the chair. You sample a sliver of the broadcast and get the same answer your friend got, because the environment cached it 50 trillion times. That's the render line. On one side, fragile amplitudes live or die by isolation. On the other, redundancy builds consensus. When redundancy is high, the UI is smooth. Move a coffee cup, and the new location is written into countless photons and phonons in microseconds. Try to catch a molecule in superposition, and the same channels tear your control to shreds unless you build careful shields. We experience the world at the redundancy level because that's what our senses and our instruments can read without collapsing everything along the way. Engineers of reality, experimentalists, learn this by scar tissue. You want to keep a superconducting qubit coherent? You trap it at millikelvin, polish filter stacks, tame stray two-level defects in dielectrics, and still, a single microvibration from a pulse tube can show up as a phase twitch minutes later. You want to see interference in a large molecule? You build beamlines that sip at vacuum and vibration isolation platforms that float like monasteries. Every stray interaction is a vote for a pointer state you didn't choose. Decoherence is relentless because the environment always has more ways to talk than you have ways to say shh. Meanwhile, redundancy buys time, not infinity. Classical records rot. Magnetic domains age. Charge traps fill and empty. Light scatters, then gets absorbed as heat and disappears into microstates you'll never reassemble. The cache refreshes itself as new interactions write new copies, but that's a dynamic balance. Push the system into a regime with fewer broadcast channels or too much competition for the same channels, and you thin the redundancy. Thin it enough, and the UI flickers. Not in pixels, remember, we're far from Planck, but in increased disagreement rates, in longer convergence times to consensus, in anomalous correlations between otherwise independent readouts. Quantum Darwinism predicts how much environment you need to see before you agree with everyone else about a pointer state. In clean models, a tiny fraction of the environment carries enough copies to convince you. In messy reality, fragments overlap, have noise, and sometimes carry conflicting snapshots because of delays and local disturbances. That's okay. Redundancy wins by numbers. But add load, more high-complexity experiments pulling on the same fragment channels, more synchronized operations with tight phase constraints, and you stress the broadcast. If a finite runtime is managing bandwidth, this is where throttling shows. The environment's ability to keep many clean, non-interfering copies in circulation drops. What would that look like in a lab? Start with objectivity tests. People already measure how independent probes converge on a common value of a system's pointer observable without directly touching the system. Increase the number of probes and the complexity of the scene. Multiple objects, overlapping scattering fields, time-varying drives, and watch how fast fragment consensus forms. If the environment is an effortless broadcaster, convergence curves are smooth, with noise you can model. If the broadcast has a budget, you see saturation. Gains from extra probe stall or cross-couplings rise in ways that don't scale with your known noise sources. Another place is macroscopicity experiments. Take levitated nanoparticles in high vacuum and try to place their center of mass in spatial superposition. People are inching toward this with optical and magnetic traps. The main enemy is environmental monitoring, residual, gas, blackbody radiation, trap noise. You suppress those, and decoherence slows. If the UI is purely emergent, you can in principle push superpositions to larger masses with engineering. If there's an unseen redundancy floor, some ambient, irreducible channel that keeps writing there or here copies, you'll hit a wall that moves too slowly with improvements, a plateau that suggests a hidden broadcaster you didn't sign up for. Then there's the meta. Redundancy requires agreement, not just within labs, but across them. Distributed sensing, interferometers on different continents, telescope arrays, synchronized quantum networks, relies on environment-mediated consistency to stitch local realities into a global map. Under load, if the render line wavers, you'd observe intermittent desynchronizations that correlate with network complexity rather than local weather. Think a day when measurements everywhere run hard mode, and the only common factor is that many high-fidelity systems were simultaneously interrogating delicate phases with aligned schedules. None of this requires a simulator. Decoherence lives in standard quantum theory. Quantum Darwinism builds on it. But the story they tell, redundancy as the basis of the classical UI, gives us a target for failure modes that don't scream sci-fi. Caches invalidate, broadcast channels saturate, copies conflict before reconciliation. If you're writing code, you anticipate that. If you're writing reality, you might too. So we set a watch at the render line. We design experiments that vary redundancy deliberately, control the number of environmental fragments you sample, modulate scattering rates, and count how much evidence you need before objectivity locks in. We log when that count drifts in ways that track global complexity, not local tweaks. And we accept a hard truth. Redundancy is mercifully forgiving, until it isn't. When it thins, you don't need a glitch in the sky to feel it. You need a calibration that won't stay put, and a consensus that takes just a little longer to arrive. Complexity overload, computation at the edge of chaos. While that was happening in clean, redundant space, another frontier was heating up. Complexity, not the vague kind. Computational complexity, the growth of operations needed to keep a system consistent as its degrees of freedom tangle. There's a reason theorists talk about quantum circuits deepening and black holes as fast scramblers. Complexity doesn't just rise, it sprints, and runtimes hate sprints. Plot twist: physics invented the original boss fight. Visual: 8-bit boss overlay as entanglement entropy graph spikes. Here's the stakes. Complexity spikes can crash systems that otherwise look stable. In physics language, you start with a small controlled state, let interactions run, and watch information spread across many degrees of freedom. In the early phase, you can track what happened. Past the threshold, local records dissolve into global patterns that only a massive, precise computation could reverse. The Loschmidt echo, time reversing a system to see if you can rewind, works for a while, then fails when imperfections grow. That failure isn't mystical, it's the bill arriving. Action first. Out-of-time order correlators, OTOCs, are the diagnostic of choice. You insert a tiny perturbation, let the system evolve, and measure how quickly operators fail to commute, how fast a butterfly flaps and a storm answers. In chaotic quantum systems, OTOCs grow exponentially before saturating, a quantum analog of Lyapunov growth. Black holes in holographic models hit the maximal growth rate allowed by quantum mechanics. People call them fast scramblers because they smear information across the horizon in minimal time. That's elegant in theory, and terrifying for bookkeeping. The faster you scramble, the sooner simple descriptions die. On-screen text. OTOC. Fast equals chaos. In labs, scrambling shows up in cold atoms, trapped ions, superconducting qubits. You build circuits that emulate chaotic dynamics, kick tops, random unitary layers, and you watch entanglement entropy rise in a light cone pattern, linear fronts that carry complexity outward. Early on, shallow circuits capture the story. Then depth requirements blow up. Small calibration errors mimic physics. Physics hides inside calibration. Certification becomes a problem of certifying your certification, a recursion that eats weekends. Impact. Complexity behaves like entropy of computation. As a system evolves, the shortest description that lets you predict its future with fixed accuracy lengthens. That lengthening is a resource drain. If a finite runtime is juggling many such evolutions, stars, atmospheres, your brain, keeping local experiences smooth while global states churn. It prioritizes where to spend steps. Smooth UI wins, exact microstate tracking loses. The symptom isn't wrong answers, it's saturation. Experiments that demand high-depth circuits hit plateaus, add more layers, and fidelity refuses to rise. That's not a bug report, it's a ration. Microstory. A group tries to demonstrate quantum advantage with a random circuit sampler. They calibrate gates to the 4th decimal place, correct crosstalk, bias T their hearts out. Early depth match theory. Output distributions pass cross-entropy benchmarks. Then, past a certain depth, the heavy output probability stops improving. They swap chips. Same wall. They simplify patterns. Performance rebounds. They return to random circuits. The wall returns. Hardware ceiling, someone says. Noise model mismatch, someone else says. Both can be true. Either way, complexity is the lever, and the machine pushes back. It's like leg day. Everything's fine until the stairs appear. Meanwhile, in gravity, circuit complexity gets a geometric avatar. In holography, proposals like complexity equals volume or complexity equals action, say the growth of Einstein-Rosen bridge volume, or bulk action, tracks the boundary state's computational complexity. Past thermal equilibrium, when ordinary entropies saturate, this complexity keeps growing for exponentially long times. The geometry inflates even when thermodynamics says done. That's the physics way of saying you can reach equilibrium and still have a rising compute tab hidden in structure you can't locally touch. Now connect the dots to the render line. Redundancy protects pointer states, but the cost of maintaining that protection rises when many systems evolve chaotically in parallel. Real life is that weather, ecosystems, traffic, neurons. The runtime doesn't need to simulate every raindrop. It uses rules and redundancy. But when we force complexity into regimes that resist compression, large, entangled circuits, mesoscopic superpositions, deep, chaotic maps, our demand for exactness climbs. If there's scarcity, scarcity bites here first. What nobody knew at the time we coined quantum supremacy was how harsh the overhead in classical side processing would be. Error decoding for big codes isn't free. Stabilizer measurements produce torrents of syndromes that must be digested in real time. Latency between cryostat and controller matters. Feed-forward timing matters. You can throw FPGAs and custom ASICs at the problem, but you move heat around more than you erase it. The classical scaffolding becomes the bottleneck. That's poetic if you're writing metaphors. It's a tax if you're building the machine. Bridge to nature's algorithms. We design worst-case circuits because they're good benchmarks. Nature doesn't. Turbulence, yes, but with symmetries and dissipation. Biological networks, yes, but with robust motifs, feedback, and modularity. The universe seems to like efficient, compressible patterns at scales we can live in. When we build devices that chase worst-case complexity, we're asking the runtime to serve adversarial workloads. That's a stress test. If the sim trims, it trims those first. So what would complexity overload look like from the inside? 3 tells. First, saturation curves. Fidelity plateaus that track circuit depth or entanglement width rather than materials limits, improve gates, and the plateau shifts a little, but doesn't vanish. Second, correlated rare events. Bursts of errors across distant parts of a device that line up with peak scrambling moments, not with known noise injectors. Third, algorithm-specific ceilings. Tasks with low entanglement growth continue to scale, while high scrambling tasks stall at smaller sizes than noise models predict. This isn't proof of code, it's a hunting guide. Complexity is where computation pays full price. That makes it the right edge to watch as we push deeper. And when an engine lags, it fakes continuity. Humans do it with saccades and memory, computers do it with interpolation. If the universe ever has to smooth over missed frames, it won't flash a warning. It'll hand us neat narratives to reconcile mismatched logs, and we'll call them memories. Human scale glitches, perception, memory, and consensus. From their perspective, nothing glitched. They just remembered the cereal box being yellow, not blue, the song lyric with one word different, the logo with a tail that never existed. The Mandela Effect became a meme because it felt like reality had patched itself. Psychology offers cleaner tools. False memories form easily when our brains compress, index, and reconstruct rather than store exact frames. That's not a failure, it's a feature. Memory trades fidelity for speed and meaning. Compression throws away detail we don't think we'll need, then guesses it back later. Stakes. First, if memory is the UI layer for your personal reality, errors feel like reality shifts, not brain slips. You don't recall an image, you reassemble it from gist, context, and expectation. Underload, stress, distraction, time pressure, the compression gets more aggressive. Confabulation stitches gaps with plausible fillers. Change blindness shows how much. Your visual system ignores when it can stitch motion into continuity. You glance at a scene that swapped colors, shapes, even people, and your mind smooths it because continuity is cheaper than recalculation. Action. Classic experiments lay out the mechanisms. Show people a crime scene, ask leading questions later, and many will remember details that were never there. Present two similar images with a brief blink between them, and observers miss massive changes unless they align attention correctly. Ask groups to recall a shared event, and watch consensus form as confident voices anchor the narrative. Each individual compresses, but the group adds a second compression. Social synchronization. We're distributed caches learning to hash to the same key. Impact. Society patches errors with stories. A rumor fills uncertainty, then repetition cements it. The brain likes redundancy too. Multiple cues, multiple modalities. If enough fragments point the same way, objectivity feels achieved. That's quantum Darwinism's intuition turned human. Many copies convince. But the copies here are in heads, feeds, and headlines. When those channels echo each other, the consensus stabilizes fast, right or wrong. Smoothness returns because we want maps that match, even if the terrain shifted underneath. Now bring in the runtime lens lightly. If the UI layer for physics is redundancy, the UI layer for minds is narrative. Both compress, both can saturate. When the environment's broadcast channels are busy, cities, networks, crises, our attention budget shrinks. We lean harder on priors. That's when microglitches feel thickest. Deja vu in fluorescent aisles, a menu item that vanishes from memory and shelf, a well-known actor you know was in a scene. Most of these are clean psychology. They're also exactly how a system would hide small mismatches, by relying on the brain's willingness to trade detail for continuity. Meanwhile, something else was happening online. Collective memory now leaves audit trails, timestamps, version histories, cached pages. Those logs act like lab notebooks for culture. When a false memory spreads, you can compare it against archives. Sometimes the archive shows you were wrong. Sometimes it reveals an actual change. Rebrands, quiet edits, regional variants, quiet edits, regional variants. The human story here is humbling. Our internal clocks are good enough to live by, not to litigate pixel-level history. We backfill. The fix feels like a glitch because the correction contradicts how certainty feels. There's a caution flag waving. Psychology isn't proof of simulation. It explains why we're easy to convince and how consensus forms. But it gives us mechanisms to detect subtle disruptions if they ever scale beyond heads. If the UI flickers at the physical layer, you'd expect an uptick in the kinds of human errors that track stress and synchronization. Simultaneous misperceptions during coordinated events, cross-lab mislabeling patterns that statistically exceed known cognitive biases, clusters of identical recall errors tied to shared timing rather than shared content. Microstory. A neutrino experiment switches run modes at noon Greenwich Mean Time. Independent teams take notes in their local time zones. Later, several groups misrecord the same parameter for a 30-minute window, despite different operators and checklists. The logs disagree with the devices, but agree with each other. It resolves as a mundane UI quirk: fonts, layout, fatigue. Still, someone adds a cross-check. Next quarter, the same pattern reappears during another synchronized mode switch across instruments that share no software. It's noise until it repeats. Then it's a reason to widen the watch. In the aftermath of every large blackout or market flash crash, investigators reconstruct timelines from fragmented human reports and machine logs. The mismatches are legendary. The lesson is not that reality blinked. It's that blended systems, people plus machines, mask small timing errors with narrative. If the physics UI ever drops a frame, that's where the stutter hides first. And our tendency to heal the story, which gives us a paradoxical tool. To catch a real glitch, you don't chase the loud memories. You build settings that reduce confabulation and demand synchronized perception across independent channels. So we use psychology as a wind tunnel. We craft tasks that stress perception and memory at the edge. Rapid serial visual presentations, synchronized cross-modal cues, distributed teams making timestamp judgments. We embed cryptographic randomness to prevent prediction. Then we look for correlated misperceptions that align to schedules rather than content. 999 times out of 1,000, we'll diagnose attention limits, expectation priors, and social anchoring. The 1,000th time, if it ever comes, wouldn't feel like magic. It would be boring data that refuses to be explained by us. And that's our cue to stop telling stories and start breaking things on purpose. Stress. Tests. How we try to break the sim. This is where curiosity turns into mischief. If the universe has a compute budget, you don't wait for a cosmic crash report. You file a bug yourself. Carefully, ethically, with controls so tight they squeak. The goal isn't fireworks. It's to load the parts of reality we think are expensive and watch for correlated strain. First, synchronize quantum load. We recruit a consortium of labs running different platforms, superconducting circuits, trapped ions, neutral atoms, photonics. For a short, pre-registered window, everyone executes high-scrambling circuits with matched depth profiles driven by a public random beacon. You can't game the beacon. It's unpredictable, verifiable randomness. Each lab logs raw outcomes, syndrome patterns, and hardware telemetry. We're not chasing success probability. We're scanning for cross-site error bursts that line up in time after accounting for light speed delays. If the runtime trims complexity under global demand, subtle, same-minute anomalies should cluster when the beacon pushes everyone through peak scrambling layers. On-screen text. Global scramble test. Second, entanglement at a distance under schedule pressure. Take loophole-free Bell setups separated by hundreds of kilometers via fiber and free space links. Normally, you randomize analyzer settings locally at microsecond scales. Here, we add a slow, global rhythm. Analyzer bases modulated by a sidereal phase, locked pattern, while the fast, random flips run on top. The sidereal lock drags our settings through a preferred cosmic frame if one exists. We ask a narrow question. Do Bell violation statistics wobble in a way that tracks Earth's rotation once we've crushed all known systematics? If the ledger maintains non-local constraints with a tiny budgeted tolerance, that wobble is where it would whisper. Third, the time hack goes loud. We coordinate optical lattice clocks, ion clocks, and microwave fountains across continents. Everyone follows a blinded, beacon-driven interrogation schedule that occasionally forces edge case operating points. Near magic wavelengths, offset by epsilon, trapped depths nudged to flirt with shifts, magnetic fields dithered within calibration bounds. The beacon injects unpredictable dwell times, so you can't pre-compensate. We're not looking for drift that one lab can explain. We're looking for near-simultaneous, species-specific phase pulls that correlate across sites and vanish when we repeat the run with low-complexity schedules. If the render line flickers, distributed consensus on seconds should be the first UI to blink. Fourth, redundancy modulation tests. Objectivity on a dial. Build tabletop scenes where many independent probe fragments, photons scattered from an object, carry information about a pointer state. Vary the number of fragments you actually sample while controlling total scattering rate. In clean theory, the fraction of environment needed for consensus follows smooth curves. Under load, if the broadcast budget thins, the amount of environment required to lock objectivity should creep upward on days when many other systems demand delicate phase information. Pair these with quiet days, pre-register, publish nulls, repeat until either the effect dies or a small stubborn offset remains. Fifth, gravitational ring down hygiene checks. When black holes merge, the newborn horizon rings like a struck bell. The spectrum should be clean, fixed by mass and spin. Teams already hunt for echoes, late-time wiggles that might hint at horizon structure. We add a twist, time coordinate the search with our other stress tests. If horizon code is a vault and global load matters, the odds of tiny spectral oddities could shift during windows when we flooded the ledger elsewhere. This is long shot territory. The payoff is the alignment, a boundary signal that sings when the bulk is busy. No joke. This is the physics version of did the lights flicker when we turned on the microwave? Micro story. Because engineers need a picture. It's a DDoS, but polite. Let's DDoS the universe isn't about breaking laws. It's about surfacing budgets. We don't pound one lab. We tap many weak points in cores, scrambling depth, non-local correlations, redundancy, timing, like a bank tester who moves $1 through all the accounts at once to see where the ledgers misreport. We move complexity through all the channels we think are expensive. Ethics keeps the rails on. We publish protocols before we run. We design so failures can only manifest as statistics, not harm. No power spikes, no radio blast, no interference with spacecraft or infrastructure. We include adversarial reviews to expose confirmation bias. We agree to post results, null or weird, with raw data for reanalysis. If a pattern appears, we rerun with independent coordination and different hardware. If it refuses to repeat, we call it what it is: noise that fooled us. What would success look like? Not memes, plots. A small, phase-locked excess error rate at peak, scrambling across 3 platforms on 2 continents. A sidereal phase in Bell violations that survives blind swaps and weather logs. A multi-species clock offset that tracks beacon schedules and disappears under low-complexity interrogation. Each alone is interesting. Together, they're a story. And if everything stays boring, that's an answer too. A runtime that doesn't flinch at our best coordinated pushes either has deeper headroom than we guessed, or there's no runtime at all, just physics being physics while we learn humility. Meanwhile, nature runs its own stress tests at scales we can't schedule. Phase transitions in the early universe, symmetry breakings, and the quiet terror of a false vacuum. Those are patch cycles we can only read in fossils. If the sim ever reboots, it won't ask our permission. But before we face that horizon, we try the knobs within reach and see if anything
early
rattles.
Universe and future fail states. 3 days earlier, something strange occurred. 13.8 billion years earlier, to be exact. The universe wasn't born smooth. It snapped into rules through phase changes. Right after inflation, a burst of violent expansion. Fields cooled and settled. Symmetries that held at blistering energies broke like ice fracturing on a lake. Each break rewrote what counted as a particle, how forces behaved, and which interactions stayed allowed. That's not decoration, it's the operating system choosing its kernel. Stakes first. If the rules can change, they can change again. Phase transitions don't politely stay in the past, they set precedents.
In condensed matter, you've seen this: water freezing, magnets aligning, superconductors flipping to zero resistance. In cosmology, the toolkit looks larger and harsher. A scalar field sitting on a high plateau can tumble to a lower valley. If the plateau is only metastable, a false vacuum, quantum tunneling can nucleate a bubble of true vacuum that expands at near light speed. Inside, constants and couplings differ. Outside, everything looks normal until the wall arrives. You don't see it coming. You don't survive the update. Action. Inflation first. A field, the inflaton, drove exponential expansion, flattening space and diluting relics. When it ended, reheating dumped energy into particles, seeding the hot Big Bang, then symmetry breaking steps. At early times, the electroweak force split. W and Z bosons got mass. The photon stayed massless. QCD confined quarks into protons and neutrons as the universe cooled further. These weren't optional cosmetics. Each transition rewrote which excitations were cheap and which were forbidden. The fossil record is in the cosmic microwave background's tiny anisotropies, in the abundance of elements, in the way galaxies emerged. Impact. Those breaks left imprints and problems. Topological defects, monopoles, cosmic strings, domain walls were predicted in some models. Inflation likely diluted most away. Baryogenesis, the matter-antimatter imbalance, begs for a transition out of equilibrium with CP violation to biased matter survival. The electroweak transition in our standard model is probably a smooth crossover, not strong enough to do the job. New physics could change that. Each maybe is a note on the system's patch history: when, where, and how the rules allowed asymmetry to stick. Now, the future-facing version. If the vacuum we inhabit is metastable, even slightly, quantum field theory says decay is possible. The Higgs potential, extrapolated naively with measured top and Higgs masses, sits uncomfortably near a boundary between stability and metastability. That calculation carries assumptions. Higher-scale physics can shift it. But the narrative is clean. We might live in a long-lived false vacuum. Tunneling would nucleate a bubble where the Higgs settles in a deeper minimum. That bubble would rewrite particle masses and couplings.
chemistry ends. Stars don't survive. No warning, no pain, just a different rule book rolling over us. That's the nightmare fail state. Crash, not heat death. The other endgame is gentle. A universe drifting toward maximal entropy as stars burn out, black holes evaporate, and free energy thins to nothing. In a lemdom-dominated cosmos, horizons fix a temperature and an entropy. The sitter space has its own Gibbons-Hawking warmth. The ledger still runs, the entries dwindle. Computation slows as resources fade. That's not a bug. That's a shutdown sequence with the fan still spinning. Bridge to our runtime frame. Phase transitions are patch cycles. Inflation looked like an emergency hotfix. Wipe the slate, smooth the geometry, reseed structure with quantum fluctuations stretched to cosmic size. Reheating was a reboot. Services back online, new version number. Symmetry breakings were feature toggles. This force splits, this particle gains mass. These interactions freeze out. The lesson isn't that someone typed code, it's that the system has modes, and mode switches leave scars. If you want to catch a final glitch, watch the places where mode switches would hurt most, whiches would hurt most, whiches would hurt most. Complications matter. We don't know the inflaton's identity. We don't know if there were multiple stages of inflation, or if eternal inflation tiled a multiverse. The electroweak transition's exact nature depends on the Higgs sector. Add scalars, and you can get strong first-order behavior with gravitational wave backgrounds as signatures. Those backgrounds are targets. Pulsar timing arrays and future space interferometers can listen for the hiss of early universe bubble walls colliding. A detection would be a smoking patch note. Version change executed at energy X. Meanwhile, false vacuum fears should be balanced. High-energy events, cosmic rays, colliders, don't meaningfully raise decay risk compared to the universe's own history. If decay were easy, it likely happened long ago. The lifetime estimates, even for metastability, dwarf the age of the universe. This isn't bedtime panic, it's acknowledging that fixed constants can emerge from a scaffold that once moved. What does an ending simulation feel like from the inside? If the fail state is a reboot, another inflation triggered by dynamics we don't control, you don't narrate it. If it's heat death, you narrate less over longer silences. If it's a mode change that creeps, you might notice thresholds slipping. Phase transitions arriving at softer energies than predicted, rare processes turning on earlier, subtle spectral lines walking faster than the bounds you trusted. The UI would hold until it didn't, then it would hand you a new one. Humor beat that isn't really funny. Update and restart, please save your work. The point isn't to scare, it's to see the story arc. Our universe has changed states before. It could again, which brings us to the user manual question. If the code can fail, how would we notice first? And what would you actually do with that knowledge? Let's be real, if there's a progress bar, we want receipts. The end user experience, signs of a final glitch. From the inside, a failing simulation wouldn't arrive with neon triangles in the sky. It would start with instruments that won't quite agree, then people who can't quite agree about why. Day to day, you'd notice recalibrations creeping closer together. Metrology labs would push firmware updates not yearly, but monthly, then weekly. The statements would sound boring. We've identified a small systematic. The pattern would feel new. The systematics wouldn't stay fixed. Start with constants that act like anchors. If the fine structure constant budges, the changes show up as tiny shifts in spectral lines. Astronomers would report a handful of quasar systems whose absorption features refuse to land on the same value after careful re-reductions. Not a drift you can point at across the whole sky, more like outliers that become stubborn regulars. Meanwhile, tabletop spectroscopy would see rare state transitions needing nudges beyond their error bars, then needing them again 2 months later. Individual instruments can be wrong. Many instruments being wrong in the same slow rhythm is different. Timing is next. The global timescale would hold, because people are good at patching, but the glue would thicken. Cross-platform clock comparisons, ytterbium to strontium, aluminum to mercury, would log more unresolved pulls, offsets that survive the usual suspects. Temperature, magnetic fields, lattice light shifts. Labs would start scheduling more frequent intercomparisons and quietly building redundancy around critical services that depend on time. GPS updates would lengthen their footnotes, the public wouldn't notice, the engineers would sleep less, cosmic rays would add a whisper. Ultra high energy events near the GZ cutoff already test propagation and interaction models at the edge. If the ledger trims detail under stress, you might see a small angle-dependent kink. Arrival directions correlated with a sidereal phase or composition inferences that wander by a notch when many observatories run dense schedules. Each detector has its gremlins. The tell would be cross-site correlations that only appear when the network is busiest. The sky wouldn't change. The statistics would. Mathematics itself rarely fails, but the machines that do math at scale can stutter.
Edge case numerical proofs, massive SAT instances, formal verifications that sit at the brink of memory would show reproducible architecture-agnostic hiccups. Two independent teams, different compilers, different libraries, both hit a checksum mismatch that disappears when the instance is simplified below a complexity threshold. You blame a library, then a kernel, then a cosmic ray, until the pattern repeats only when the instance crosses a depth you can dial like a knob. In quantum hardware, fidelity plateaus would stop retreating. For a while, better materials and cleaner control push the ceiling up. Then the ceiling holds even when known error sources fall. Syndrome logs would show bursts that line up with peak circuit scrambling, and those bursts would align across labs when they run coordinated stress sequences. When the same device runs simpler, low entanglement tasks, it sails. When it runs tangled maps, it wheezes. That split already happens because noise is real. The shift would be in how the ceiling shrugs off every incremental fix. At the classical UI, you wouldn't see pixels, you'd feel friction. Consensus would take longer in places that once converged quickly because redundancy would thin in subtle ways. High-end interferometers would report more frequent glitch veto windows, where environmental monitors disagree about whether a disturbance occurred. Radio arrays stitching long baselines into sharp images would schedule extra calibration blocks and still accept slightly blurrier reconstructions on busy nights. No one headline, a dozen small changes in operating procedure, all pointing to higher costs for the same confidence. Human logs would echo the machines. Flight calendars would tighten margins on precision approaches because local augmentation systems add extra integrity checks. Finance might see a rise in micro desynchronizations between exchanges that clears with new patches, then returns when traffic spikes. Hospitals would notice certain imaging sequences needing more repeats to hit diagnostic quality. Not everywhere, not always, but in clusters that map onto days when a lot of precision devices run in sync. Big physics campaigns, networked observatories, time hack weeks. Scientists would talk differently in the hallways. It's probably us, because it usually is, followed by, but why does it go away when we back off complexity? More preprints would end with longer sections on unresolved systematics and a promise to revisit with larger collaborations. Conference sessions would sprout coordination tracks whose talks sound like systems engineering manuals. The vibe wouldn't be panic. It would be unglamorous persistence, holding the UI together with more glue than you used to need. For you, the end user, it lands as a drip. Your phone's map is fine. Your lights turn on, flights still fly. The strangeness is ambient. Updates come faster, devices recalibrate more, services ask for patience more often. If you look closely, you'd see that the patience clusters around precision, around edges where reality meets rounding, and if it's real, it won't stay a drip. Conveners will call for synchronized runs, and the anomalies will either fade under better discipline or brighten under load. If they brighten, consensus breaks fast, not into chaos, but into work, 1,000 hands pressing on the same seam, listening for a sound only the careful can hear. Ethics, agency, and meaning if it's all code. While the careful people listen for that sound, a harder question waits under the noise. If this is code, what does that make us? The temptation is to punt, say it doesn't matter. But it does, because ethics runs on assumptions about agency, responsibility, and value. If freedom is just a rendered feeling, does kindness still count? Start with agency as interface. You experience choices as options on a screen you can click. Underneath, the runtime enforces rules, probabilities, and constraints. That doesn't make the click fake, it makes it implemented. In every system we actually trust. Planes, hospitals, cryptography, interfaces make control usable, while deeper machines guarantee consistency. Moral agency in a coded world works the same. You own the part of the loop you can steer, and the loop still lands planes. Moral realism gets a similar translation.
If values are simulated, are they arbitrary? That depends on how the runtime scores outcomes. Even inside code, trade-offs have consequences. Pain harms adaptive systems. Cooperation stabilizes groups. Truth makes prediction better. Those aren't decorations, they're convergences. Biology, economics, and engineering rediscover them because they're useful wherever signals are noisy and resources are finite. If you label those regularities ethics, you're not making them up. You're measuring what keeps agents thriving in a world that pushes back. Practical test. Try cruelty. It burns trust, fragments redundancy in relationships, and collapses future options. Try honesty and curiosity. They increase shared bandwidth and lower coordination cost. In runtime terms, kindness still compiles. Curiosity still pays. You don't need metaphysics to see it. You need feedback and time. Free will, then. If you're a process, are you free? The old fight assumes freedom means uncaused sparks. That's not how control works in any real system. Freedom is the width of the corridor. You can walk without the walls closing in. Better models, more memory, and richer signals widen that corridor. Ignorance narrows it. Agency becomes the art of expanding your predictive horizon enough to steer, even when the floor is laid down by rules, meaning follows. If everything ends as heat or the sim shutters, what's the point? The point is local. Build pockets where complexity can persist, where experience is rich and suffering is minimized, where tools and stories let others steer better. That survives version changes because it's adaptable. If the runtime updates, kindness remains a good bet. If it ends, the bet paid while you had it. There's a lighter beat in this. Be nice to NPCs. You might be one. The joke lands because it cuts both ways. Treat others as fully real even if you doubt the substrate. That rule preserves value under uncertainty. It also insulates you from the ugliest failure mode, using the "it's all code" card to skip responsibility. That move always backfires. Systems punish it with isolation, law, or simple mistrust. Agency as interface also suggests a discipline. Keep your drivers updated. Train your attention. Test your beliefs against data. Build habits that reduce harm when you're wrong. Version yourself deliberately. In a universe that might be optimizing, align with the parts that stabilize good futures. Error correction, redundancy, transparent logs, generous defaults. Those patterns show up in physics and in communities. Adopt them. And truth-seeking? Whether or not we're in a sim, finding how the world resists you is the only way to get better at not breaking it. We've spent an hour building instruments to hear seams. The ethical mirror is the same. Learn your biases, publish your methods, pre-register your predictions, and invite people who disagree to test them. You gain resilience. You also make it easier for future you and future us to keep steering if the UI gets slippery. Bring the existential bite back in quietly. If code can fail, then urgency isn't about panic. It's about practice. You will not debug a universe. You can debug your corner. That's meaningful work under any substrate. The scariest part isn't that reality might be code. It's that all code at scale can fail in quiet, human-sized ways first. Today we tied hard science to testable signs. C as the processing cap, horizons as bit budgets, black holes as garbage collection, and clocks as the UI that could flicker first. If you want to see whether there's an escape hatch or just a falsifiable test that clears the fog, watch the next one. We're building the experiment and the ethics around it. Subscribe and bring your skepticism. We'll